Today is lecture number what? Okay, so Happy New Year for those of you. Okay, I don't know whether this class any tiger or not in this class. Any tiger in this class? Any tiger? No tiger. Huh? Got at least one tiger, is it? Then who are the other animals in this class? Rabbit, Okay, before we start, I just ask any last questions on homework 4, which is due 11:59. I saw some people already submitted. Anybody have any questions on homework 4? Is homework 4 very easy? Chicken is it? Okay, the reason why is a bit difficult because I took the questions from last year's final exam. Okay, so this will give you some idea of the difficulty of an open book exam. So EE5507 is an open book final exam. Okay, so obviously the questions have to be a little bit more challenging. Okay, all right, but I will try to give you some hints in the question. Right. Okay. Okay. Some of you, I think I'm quite happy. A lot of you ask questions, so I compile the question and put it onto the Luminous so everybody can see. Okay. So if you have questions, please don't worry, just ask. Okay. There's no such thing as a stupid question. Okay. There's such a thing as an ineffective professor. Okay. All right. But there's no such thing as a stupid question from a student. Okay. Let me just see. Okay, so Professor Heng, I think, is still on medical leave, so I'm not exactly sure when he's coming back. Could be next Monday, maybe. I don't know. All right. So for the time being, we just proceed along this way. Initially, my thinking was that part 1 and part 2 is not closely related, okay? But I realized from the question that you asked from the homework, actually there is some relationship between part 1 and part 2, okay? Especially things like transfer function, all right? What is the meaning of the omega p, the pole frequency, the unity gain frequency. So this, I think, is covered actually in part 1, but this also should have been covered in your undergraduate electronics class, correct? The op-amp, what is the pole, what is the unity gain, all this, all right? So, yeah, so, I mean, there is some link, but hopefully the linkage is not too great, okay? All right? Okay, so no questions, No questions, Okay, so let me repeat, The homework due just before 1 minute before midnight tonight. Okay, so please submit. All right. For the homework, actually, to be honest, I don't mind if you all discuss among yourself. Okay, you can discuss, you can learn. Okay, but please, after you discuss, you have to write out the answer yourself. Okay, all right. That's part of the learning process. Okay, please do not discuss and then one person write and everybody else just copy. Okay, you are only cheating yourself, okay. That's all I can say. Right. So the important objective of this class is to learn. Okay, is to learn. That's the most important thing. Right. Okay. So let's go on to today's topic. So today's topic actually is an interesting topic. Okay, because noise. All right. So all the other topics that we talk about today are in part 2 are all circuit building blocks. Okay, data converter, filter. Later on we'll talk about comparator. We'll talk about what else? Oscillator. All those are building blocks. Okay. The only topic that's not a real building block is this topic of noise. Okay. And what's the reason why you want to learn about this topic? Because it's a very important topic. Okay. How many of you have encountered this topic before, noise, in your previous courses? Anybody? Noise? See, silence, no noise, silence. Okay. So noise actually is quite an important and basic concept in electronics. Okay, and we need to understand. Okay. Remember in lecture 7, we talked about the ADC and we talked about this thing also called a noise, the quantizer noise. Okay. Actually, from today's definition, today's class definition, you will know that that is not 100% accurate. Okay, because the quantizer error, which we call noise, is not really statistical random noise. Okay, the quantizer error is quite predictable. All right. So, but we use the term noise because of the analysis and all that. Okay, but today's topic, noise is really noise. Okay, and what we will do is we'll go through it. But before that, as usual, I want to just do a quick recap review, especially since we have 2 weeks due to Chinese New Year, right? Okay, so the last lecture we talked about filters, all right? What did we cover? What are the specs? What are different frequency response on the filter? Omega P, which defines the what band? The pass band, right? And omega S, which defines the start of the stop band, okay? And then these two terms, alpha max, alpha min, okay? What do they mean? One of them is talking about the maximum ripple in the pass band, and one of them is talking about the minimum attenuation in the stop band. Okay, so you look at the example, example, don't know what lah. You will use these terms, okay? All right? Okay? One of you also asked during the question that how come, how come we need to know what is the omega S for the filter order? Okay, the one I explained to you all, right? The filter order depends on the transition between the pass band and the stop band. Okay, so the sharper the transition, the higher the order. All right? Okay, that's why you want to define a filter with a very, very sharp cutoff. Okay, you need a very high order complicated filter. Okay, all right? Okay, so the filter transfer function, we talk about the magnitude and the phase. Okay, we talk about this thing called group delay, which is defined to be change of phase with frequency. And the only meaningful thing about this is that it means that if you have a constant group delay, there's no distortion, right, when the signal passes through. Okay. Then in filter design, because we are using a lot of tables, all right, which are generalized, we need to have this idea of scaling, all right, and normalization. Okay. So in a lot of the tables, in the textbook, all that, omega p is defined to be 1. Okay, and then everything else scales accordingly. Right? So when you use a table, you need to know, after you have designed using the table, you need to denormalize for your actual filter response. Right? So if your FP is 10 kilohertz, you need to scale all the things by 10K. Okay? So there's scaling in the frequency side and also magnitude scaling. Right? And normally what we will work on a normalized transfer function. The subscript n is normalized. And then after that, we will scale it to pick the actual component values. All right. So when you implement a filter, we are using resistor, capacitor mainly. All right. So when you first design it using the normalized transfer function, you get certain values. All right. Those are the normalized Rn and Cn. Then after that, you need to scale it, right, for more practical values. Okay, you cannot have a capacitor which is 1 farad. Okay, 1 farad implemented on an IC chip. Okay, it will be huge. Okay. Okay, then we talk about first order filters, which we call the bilinear. Remember the bilinear filter? Numerator, denominator. All right, you have 1 0 on top, 1 pole at the bottom. Okay. So even though it's quite simple, but for a different combination, you can get high pass, low pass, all pass kind of circuits. Okay, so you can implement it using passive components, which is basically R and C, or you can use the active component, which means use the op-amp. Okay, right? And the design methodology is that you have to find, or you're given a transfer function, and you need to find all the related pole zero location. Okay, and then finally we talk about this thing, what happens when the op-amp that you use is a non-ideal? Okay, so when you first analyze it, you analyze using ideal op-amp, right? Ideal op-amp means what? Gain is infinite, right? So virtual ground, right? Gain infinite. How? Bandwidth? Also infinite. Okay? Right? So everything is infinite. Input impedance also infinite. Okay? So that's the ideal op-amp, okay? But obviously in a real circuit, there's no such thing as an ideal op-amp lah. So a real op-amp will have some properties. Gain cannot be infinite. The frequency bandwidth cannot be infinite also. Okay? So all these are the non-ideal part. Alright? And then you can analyze it when you look at the circuit and have a real op-amp inside there. Okay? So as a minimum, we will say, okay, this op-amp has a gain of so much. Alright? Or we will just say that this op-amp has a gain function A of S. Okay, and in this A of S, there will be a DC gain, there will be at least one pole, right, to define the bandwidth. Okay, that's the simplest real op-amp model. Okay, and you look at some of the examples, you can see how to analyze it. Okay, so one of you also asked a question, right? So actually, it's very simple lah. Okay, if you have a real op-amp with a gain of A, it means that the output equals the two op-amp input multiplied by A. Okay, that's the definition, right? Input of M, how much is the input? Multiplied by A will give you the output. Okay, so in the extreme case of ideal op-amp, when the gain is infinite, the output is finite, it means that the input must be 0. That's why we have the virtual ground. Okay, alright, okay. Okay, then we'll also talk about different other type of filters. Not only the bilinear, but the biquad, okay? Biquad transfer function. This can be implemented using 3 op-amp, okay? And normally you will have, this will be a system whereby you have under constraint. That means you have only 3 design equations, but you got 6 unknowns. So you have to choose 3, alright, and then find out the other 3, okay? Okay, finally we talk about this special type of filters which are called the maximally flat response. It means the passband is flat. Okay, it is flat. Okay, remember we have this term called the alpha max, right? That describes the passband has a ripple. Okay, but for this maximally flat filter, passband is flat. Okay, and then it only drop off at the W omega p. Okay, right? So we talk about what it means to have a maximally flat response, what the transfer function look like, alright, and then how to obtain the transfer function from the tables, and then how to implement this, alright. If a low pass maximally flat filter or with Butterworth filter, we can use the Salem key circuit, just map the values, okay, back to the transfer function. And for the design methodology, once again, 3 design equation, and sometimes you have to adjust the gain, okay. And then this one came out in example 2.3, is that when the passband H is not at minus 3 dB, it means that it's not a Butterworth filter. Okay, all Butterworth filter passband H omega p, the transfer function magnitude is down by 3 dB. Okay, independent of whether it's the order 2, order 3, order 4, order 5, order 6. You look at the slide, it shows you every single Butterworth filter at omega p or fp, it will be at minus 3 dB. Okay, right? So in example 2.3, okay, when you have given a case whereby the alpha max is not minus 3 dB, okay, this tells you straight away that it's not a Butterworth filter, but it's still a maximally flat filter. So the equation that you use is slightly different. Okay, there's the epsilon term, right? It's one. The denominator is 1 plus epsilon. Okay, omega squared. Okay. So that one there's a trick that you can play to do some scaling, right? To transform it in the frequency side back into a Butterworth filter. Okay. Okay, so that was the review of filters. So today what we will talk about 4 things, okay? 1, how to analyze noise, okay? Then we'll talk about why there is noise, okay? What are the sources of noise and what are the models? And then we talk about noise estimation. And finally, we'll talk about some techniques to reduce noise, okay? Okay, so under the basics of noise analysis, we'll talk about what is noise, define noise, how does noise look in the time domain, the frequency domain, what are different types of noise, how do we characterize or measure noise, and how do we do a performance evaluation, okay? Okay, so this is quite a general definition, right? Anything that's unwanted, okay, unwanted, okay, from what the real signal is, you just consider it noise, okay? This is very general, huh? So it can be a random interference, thermal noise. It can be noise from the power mains, okay, power mains, right? So if you actually go and measure the power mains, of course high voltage, don't just go and poke a wire there, okay? But if you somehow measure the power mains, you will see that there's a noise. And what is this noise? Why is there a noise there? It's because the power is transmitted, AC or DC? AC, right? AC, huh? So there's a frequency, huh? By the time it reaches here, is what's the frequency? 50 or 60, right? I forget. Okay? Some countries 50, some countries 60, like, depending on the last transformer in the substation. Okay? All right? So if you're, this is an interesting story. If you all watch the movie on Tesla, on the this person Tesla, not a car, okay. So I think in the early 20th century, I think, right, there was a big debate and war, okay, when they wanted to transmit electricity long distance, okay. What was the best way to transmit it? So on one side, you go watch the movie. On one side, you have a very famous inventor. What's his name? Edison, Thomas Edison. Okay, Thomas Edison said, okay, transmit DC. Transmit DC. Transmit the electricity as DC. Whereas on the other side, you got Tesla. Tesla said, no, transmit AC. So there's a big fight between two of them. They set up two different companies and try to. All right, in the end, who won? Yeah. Actually, Tesla didn't win. He went bankrupt. You watch the movie, he went bankrupt. Okay? But the technology won. Okay? Because there are certain advantages when you transmit AC in terms of power loss and all that. Okay? So that's why today everything is AC lah. Okay? Alright? Okay. So, okay, then the spectral interference, okay? There could be flicker noise, aliasing, or there could be interference from different signal, okay? You have signal 1 kilohertz, another signal 5 kilohertz. But somehow in the circuit, 5 kilohertz may be downshifted to 1.5 kilohertz or whatever, okay? So all these are all the different. So noise, there are different types of noise. And noise basically is described mainly by its properties, okay? So what we will say is that sometimes we say the noise is a white noise. Okay, what's the meaning of this? Okay, white noise basically means that it comes from the frequency characteristic of noise. Okay, that means the noise is present in all frequencies. So it's light lah. When you say white light, it's because all colors are there. Okay, so that's why they call it white noise. Okay, it's not that you see the noise actually white, but because from the frequency domain is across all the frequency band. Okay, and we will see later on, all right? And then you have flicker noise, which is concentrated in the low frequency side and drop off, okay? Okay, so we can see noise in both the time and frequency domain, okay? So this means that if you have an oscilloscope and you probe a certain point in your circuit to try and measure some voltage or whatever, or some current, you may see something like this. Okay, you don't have a constant value. Okay, you have things moving around. Okay, and when this happens, okay, is either your connection is not good, okay, or it could be the circuit is noisy, right? So the noise will show up as fluctuations, okay? So we will define, for such a noisy signal or noise signal, we can define its properties, okay? And normally we will not just take the average, because the average could be 0, okay? Because if it's a random signal, right, the average could be 0. Just like a sine wave. If I ask you what's the average value of a sine wave, it's 0, okay? But the noise has got power, okay? So how do we measure this? So what we do is normally we will take the mean square value, all right? We take the square and take the mean, okay? Take the square, integrate the voltage squared of this signal over a certain time, divide by the time, this will give you the power, okay? And then from here, we will define what is the RMS or root mean square value, okay? RMS, okay? That means square root of the mean power, of the mean square, okay? Right? RMS means square root of the mean square, okay? So here, right, VNT is your noise signal. I take the square, okay? I find the mean square value, okay? Integrate OT divided by T. Then I take the square root, okay? This is the definition of RMS. Root mean square, okay? Can be voltage, can be current, all right? Okay, and then now we come to this concept again, normalize again, normalize. Normalize means refer to something, okay? Refer to something, right? So power is V squared over R, right? Voltage squared over R. You all know how that comes about, right? Why is power V squared over R? Sorry? Yeah, because you use Ohm's law, okay? Okay? Power actually is voltage times current, okay? That's the general definition of power, right? Voltage times current. And then if you apply Ohm's law, current is what? Is voltage divided by R, okay? That's why you get P equals V squared over R, okay? Or P equals, the other way around is P equals to I squared R, okay? All right? So there's an R there, and what we can do is we can say, okay, we will reference everything to 1 ohm, okay? Just treat R equals 1 ohm, okay? Okay, so when we deal with noise, how do we combine noise, right? Okay? So because of noise power and because the noise average is 0, okay, when we combine noise, we will normally combine the noise power and not the noise voltage or noise current by itself, okay? All right? Okay? And we can only do this, okay? So you see here, the output, in this case, this is output, okay, you have 2 noise sources there, okay? If you just add the 2, sometimes you may get 0 because they may just cancel one another. Okay, one could be plus 2, one could be minus 2, and then you get 0, okay? But if you add the noise power, okay, right, which is Vn1 plus Vn2 squared, okay, you will get this, right? You have a square of Vn1 squared plus Vn2 squared plus a product of the 2, okay, plus a product of the 2. Now we come to this definition, very important definition to understand, is that we want to say if the 2 noise source is what we call independent or uncorrelated, they're independent of one another, okay, then we can make the simple, then we know, right, that because they're uncorrelated, this product is 0, okay, and therefore what remains is only the individual squared terms. Okay, and this is something we will use very often, okay? When you have a circuit with many different noise sources, and we want to find out, okay, what is the output noise power? Okay, you need to combine all the noise sources, right, to the output. Okay, very often all these circuit noise sources are all uncorrelated. Okay, so you can, at the output, you can just add the noise power. Okay. Okay, so this is the noise power summation, all right, either in the voltage domain or in the current domain. Okay, but important assumption is that this is uncorrelated, right? Okay, that's the important assumption. So you have two transistors, normally the noise sources are uncorrelated. Okay, transistor M1, transistor M2, all right, they are independent. Therefore, you can combine the noise power. Okay. Okay, so we come to the first example, right? How do we add noise sources? Okay, so straight away, we have two uncorrelated noise sources with their RMS values. Okay, what is the total output RMS power when you combine it? Very simple, right? So we know I just add the noise power, right? 10, this is VN1 RMS is 10 microvolt, VN2 is 5 microvolt, just 10 square plus 5 square. This is the square, the sum of the square. And then you just take the square root, you get the RMS of the output. Okay, very simple. Okay. Okay, second part of the question. If we want to maintain total output RMS at 10 microvolt, okay, how much should VN1 be reduced without changing VN2? Okay, so you just use this equation again. All right, you want the output RMS to be 10. That means the square is 10 square. And then you don't want to change VN2, right? You just want to change VN1, right? You can work out that so VN1 has to be 8.7 microvolt. Okay. Okay. So here you can see that a very simple principle, right, is that if you're asked your circuit is too noisy and you want to reduce noise, what should you do? Common sense is find the biggest noise source and reduce that one. Okay, put your energy to reduce the biggest contributor. Don't go and find the smallest one and then try to optimize it. Okay, okay. Okay. So we saw that in the time domain, the noise looks random, okay, just a lot of funny up and down curve, okay. But if you look at it from the frequency domain, okay, we see something different, okay, see something useful, okay. So in the frequency domain, we call this thing called a spectral density of noise, okay. Spectral density, okay. Some people use the term PSD, power spectral density, okay. So what is this? What is this power spectral density? Okay. PSD has got units of volt square per hertz. Volt square per hertz. That's why it's called a power spectral density. Okay? So you may see a curve like this. Okay? This is the PSD curve. Alright? So each point of this curve will tell you what is the noise power spectral density. Okay? So for example, at 100 hertz, okay, at 100 hertz, you could have a noise power spectral density of about 10, all right? 10 microvolt square per hertz, okay? Now, what is the use of this? Well, the use of this is that if I want to ask you what is the total noise, okay? All right? And I give you the frequency bandwidth. All right, then you can find out from this graph. How? You just integrate what's the area under this curve. Okay, so you want to find out what's the total noise power between 0 and 1000 hertz. You will just integrate from 0 to 1000. Okay, right? And what's the unit you will get? What's the units you will get? PSD is volt square per hertz. Once you integrate, you multiply by hertz, you'll be left with the volt square, okay, which is the mean square. All right? Then from there, you can calculate what's the RMS value very easily. Just take the square root. Okay? All right? Okay? Okay. So from the PSD has a very close cousin. The cousin of the PSD is the RSD. Okay? Which is the root spectral density. Okay? Which basically means take the PSD, take the square root. Okay? Take the square root. Okay? So now the RSD, the unit is not volt squared but volt, because you take square root and per square root hertz. Okay? Right? Okay? So the units are like microvolt per square root hertz. Okay? Okay, so basically, again, to find what is the noise mean square, you basically just integrate below the PSD curve. Okay? And if it's a current curve, same principle. Okay? So noise, you can say what's the noise voltage, what's the noise current. Right? Okay, so now to twist your brain even further, right? Okay? So you can look at noise from time domain, frequency domain. Okay? So for example, in the time domain, right? Here is the noise voltage. Over time, you can see a lot of different curves. Okay? All right? For example, all these actually all these curves are all different sine wave. Okay? Right? So in the time domain, it looks like a sine wave. 1 sine wave, 2 sine wave, 3 sine wave, 4 sine wave. All right? And then basically what we do is, in the real time domain, I will just add up all the different sine wave. Right? Okay? Once I add it up together, depending on what's the phase relationship, you may not be able to tell that it's this is a series of sine waves. Okay? But if you go and take the spectrum, frequency spectrum of this noise signal, all right, you can see clearly that it's a series of sine waves. Why? Because in the frequency spectrum you see all these tones, right? So you know, if I give you a sine wave and I ask you what is the frequency spectrum of the sine wave, what is it? It's just one line, right? It's one. What's the term for this? It's a one delta function, okay, at the frequency, okay. If it's a pure sine wave, a pure sine wave is just a single tone. 1 kilohertz sine wave, one tone at 1 kilohertz. Okay, all right. That's why frequency domain is a useful way to analyze it. Okay, because if I just add up all these sine wave and I show you the waveform, you may say, well, this I don't know what this is. Just random thing up and down, right? Okay. Okay, you know, in the lab, how would you do this in the lab? Now I give you a circuit. I say this is the output. Go in the lab and see time domain, frequency domain. How you do it? Okay, time domain first. Time domain. I give you a circuit. Ask you what's the time domain waveform of this thing. How will you do it? You go to the lab and connect up the oscilloscope, right? Connect oscilloscope. Oscilloscope will sweep the x-axis in time and show you how the signal is changing in time. Okay? How about frequency domain? What? DFT? No, in the lab. In the laboratory. I give you a circuit now. Okay? I say, okay, this is a circuit. This is the output point. Right? Go to the lab and show and find the frequency response. Use the spectrum analyzer, right? It's a spectrum analyzer. Okay? That is similar to the oscilloscope, except that you will sweep frequency. Okay? Alright? So anybody know how this spectrum analyzer works? Okay, it's very interesting. What they do is, how do they have to, the spectrum analyzer has to go and find out what is the signal power at different frequency, right? In order to plot this thing out. Okay? So what you will do is that inside, this, I don't know whether it's, okay, last time it's HP, now it's not HP, now it's Agilent or Tektronix or this guy, right? So what they will do is they will have a series of bandpass filter, right, for each frequency bin, so that they can extract out what is the signal power, and then they will display it. Okay? Okay, so analog circuit is hardware, okay, hardware. So hardware, you must be able to know how to measure. Okay? All right? Okay, okay, again, time and versus frequency. Okay? Okay, once again, this is, if you have a very noisy signal like this, and the time domain, maybe you can't tell, you can't have any meaningful information. Okay, maybe you can see that, okay, maybe there's an offset. Offset. The signal is not relative to zero. Okay, there's an offset. Okay, right. But if you do the frequency domain, right, which you can do, this lady students, right, do FFT, right? FFT is also getting a frequency response information. Okay, all right. Yeah, then you will see clearly, right, that this so-called time domain signal actually has got some interesting frequency properties. Okay, here it has an offset. Okay, it has one sine frequency here, second one here. Okay, all right. Now, I mentioned previously, right? Sine wave only one line, right? How come it's like this? How come it's like this? Yeah, so these are the interesting questions you should ask, okay? Right, between theory and measurement. Because you learn a lot, right? Yeah, so how come? Noise, okay, not noise, not noise, okay. Good try, okay, good try. It's not noise, okay? So actually it's interesting, okay? This is due to windowing. Windowing, okay? So, okay, how many of you know how to use FFT? Okay, so FFT is a algorithm, right? It's an algorithm to FFT stand for first. Fast Fourier transform, right? Okay, so FFT is basically it's a fast way to compute the Fourier transform. Okay, the Fourier transform. Okay, the Fourier transform will tell you what's the information on the frequency. Right? Okay, anyway, when you want to perform the FFT, you need to take samples. You need to take samples. Okay? But when you take the samples, you have to define the time window. Okay? Right? Because you cannot take infinite, right? So you define a time window to take all the samples. Okay? Now, if you have pure sine wave, okay, you must have the right time window. Okay? If you have the right time window, you will get a nice tone. Okay? If you don't have the right time window, you may not get the result you want. Okay? So if you go and Google how to FFT and windowing, there's a lot of information there. Okay? So depending on what the frequency you're trying to measure, what is the window you should use. Okay? So if you don't do anything, you just happen to have a rectangular window. Yeah, I start from this time, start at this time. Take all the samples. Okay, that's what I call a rectangular window. Okay? But you have to choose your start point and end point window very carefully. Okay? Depending on the signal frequency you want to measure. Okay? Of course, that's very difficult, because if you don't know what's the frequency, how to do this, right? So that's why people have different kind of windowing technique, right? That means instead of taking a rectangular window, they have all kinds of different windows, Henning window, a lot of different windows which basically shapes the time samples. Okay? And that's the reason why when you apply this kind of window, even though it's initially is a single tone, some of the energy gets spread out. So you see something like this. Okay, right? But since we know it's due to windowing, it's likely that there's a tone there. Okay, all right. You don't believe me? You go and Google and read out some of the textbook. Okay, on FFT and windowing. Okay, it's an important topic. Okay, so when you look at any FFT result, normally they will tell you. Okay, they will tell you what sort of window they apply. A Henning window, a Hamming window, or whatever window. Okay. Okay. Right, so you can see here again, okay. So now let's say I have two signals here, okay. I have two signals here, all right. Obviously, you can see that these two signals are shifted, they are shifted in the time domain, okay, which means that there's a phase difference, okay. If you look at the frequency domain, you can't tell, because the frequency domain just tell you that what the frequency content. Okay, they don't tell you about what's the phase information. Okay, okay. So the frequency domain magnitude power spectrum doesn't include phase information, right? That's why sometimes you need to see the signal in both time domain and frequency domain to get all the information out. Okay. Okay. So now we're going to talk about different types of noise. Okay. Okay, so the first type of noise we're going to talk about is what we call the white noise. Okay, white noise, I told you, is because it's the noise spread across a wide frequency spectrum. Okay, so the term comes from optics. Optics. White light has all different colors. Okay, black has got no color. Okay, so a lot of you like to wear black nowadays. I don't know why. This Singapore wear black no good, no? Absorb heat, no? Black body radiation. No? Okay, white reflects heat, okay? All right, so that's why I see a lot of buildings, they want to save energy, right? They'll paint the wall white and they won't paint the wall black, because the black is a good absorber and also a good radiator, from physics, black body radiation, okay? Okay, so white noise means that the noise power is independent of frequency, that is a very wide band frequency, okay? Okay? And furthermore, we say that the frequency spectrum, the PSD, is flat. It's flat, okay? And later on, we'll see that in some of the electronic devices that we want to study, the transistors, there's a part of the noise that is white. Okay, that's what we call a thermal noise. Thermal noise, okay? Okay, so for this one, very simple. What is the noise power in a certain bandwidth? Just take the PSD, multiply by the bandwidth. Okay, so here is the first important thing to remember, okay? When we want to calculate or analyze noise, the most important thing we need to know, apart from the characteristic of noise, is we need to know what is the frequency bandwidth that we are considering. Okay? Now, you may ask why we want to do this. Okay, the noise is wide, what? Very wide bandwidth, what? Right? But in our circuits, right, it's always limited in the bandwidth. Okay? Whatever circuit is limited, okay? Even the op-amp we design, okay, is limited in bandwidth. Okay? We don't have a circuit which is infinite bandwidth. Okay? Right? So all the circuits that we have always have a finite bandwidth, and therefore this finite bandwidth will define what is our noise bandwidth. Okay? So even though our circuit, transistor, MOS, bipolar, all this, right, has got noise sources which are wide, which means infinite bandwidth, but once it goes through our circuit, it will be band limited. Okay? Because our circuit is band limited. Okay? What's the best way to explain this? I don't know. Maybe, let's say you have a very old car. You have an old car, right? It can only go to maximum 50 miles per hour, right? So you go to a petrol station, the petrol guy says, oh, please pump this premium grade petrol, okay? It will allow cars to go to 100 miles per hour. Doesn't matter, your old car only can go maximum 50 miles per hour. I give you a high grade petrol, right? Your car can only go 50 miles per hour, right? In fact, it may explode. If you try to give it too much power, it may explode. Okay? So this is a simple analogy, all right? Okay? So when you calculate, when you ask to calculate noise, circuit noise, always you have to know what is the bandwidth. Okay? Because without this information, you cannot calculate the noise. Right? Okay? Okay, that's for white noise. Okay, second type of noise is what we call the flicker noise. Okay? Now, why? So where does this name flicker come from? Okay, I think it's historical. So flicker means on, off. Okay, flicker, right? Something is flickering. A light is flickering. It means that sometimes on, sometimes off. Okay. So I think the history of this is that when people first saw this noise in the time domain, okay, something can pop up and then go off, disappear, pop up and disappear. So they call it a flicker noise. Okay. And then when they look at it from the frequency domain, then they found something. Okay, what did they find? That this noise actually has a sloping frequency component. Okay, it's higher during low frequency, and then it drop until a certain knee, and then it disappear. Okay, so that's why flicker noise is also is sometimes called 1/f noise, because you got an inverse frequency dependence. Okay, so in the frequency domain, you will see something that drop the frequency. Okay, and then after that, it will drop to very small values, and then your circuit becomes dominated by your white noise. Okay, all right. So for example, in this graph, if there are two noise sources there, right? One is your white noise here, flat across frequency. One is your flicker noise. That means at low frequency, the flicker noise is much higher than your white noise. That's why you only see the 1/f. Okay? At high frequency, the flicker noise becomes very small. You're dominated by the white noise. And here, where the intersection, we call it a corner. Okay? When the flicker noise equals the white noise. Okay? So this graph, once again, is a straight line approximation. Okay? Like the Bode plot, straight line approximation. Okay? The actual thing has got some, will have not a sharp corner, but will be quite gradual. Okay? Alright? So just like a filter transfer function, right? Straight line approximation, Bode, alright? Straight line. Pole, come down, minus 20 dB per decade, whatever, right? Okay? So this also, okay? Minus 10 dB per decade, straight line approximation. Okay, then band limited noise, okay? So this is what I told you, right? We have a noise source, you go through a real circuit with a certain transfer function. The output noise will be whatever is the input noise multiplied by the transfer function of this guy. Okay? Alright? So because noise power, you take the amplitude square of the transfer function. Okay? A to the j omega or A to the j 2 pi f is the frequency of the transfer function. Then you take the magnitude and you take the square. Okay? And the RMS noise is you take the square root of this. Okay? So if you have a circuit like this where you have three different transfer function, and then you combine all together, you just sum all the noise power of each of them. Okay? And then you take the square root to find the RMS. Okay? So noise power is quite simple to understand. You assume that it's uncorrelated. You take the noise power, which is V squared or I squared. Okay? And then take the square root. You want to know what is the RMS value. Okay? This one no need a lot of mathematics on. You just need to know how to add and take square root. And also know what is the bandwidth. Okay? Okay. So here is the idea of this noise equivalent bandwidth. Okay, so now we say we need to know the bandwidth, right? So how do we find the bandwidth? Okay, so here is where we do some mathematical approximation or simplification. Okay, so for example, if your H of S has this kind of a single pole response, it's an op amp with a single pole, right? Passband flat, DC gain, and then hit a pole, all right? The magnitude response drops, minus 20 dB per decade. Okay, so it's like this, the body approximation is like this. Come to the FP, it will drop like this, okay? Minus 20 dB per decade. Now, if I pump in a white noise at the input, and what will be the output noise power? Input is flat. You go through this transfer function. That means only the area under here, right, will be the noise power, right, that can go through. Okay, but it's a bit not easy lah. So you need to integrate this kind of a function, this curve, right? So people say, okay, how can we simplify things? Okay, so the simplified thing is, okay, what is the so-called rectangular or brick wall approximation to this? Right? What is the so this is the area we want. What is the equivalent area of a rectangle of this same area? Okay? And so basically what you can do is you take this single pole, right? You go integrate it. Okay? Integrate it, you will find that the equivalent brick wall, okay, has a limit frequency fx. Now fx obviously is greater than your fp or f0. Okay? Because here, right, from f0 onwards, there's some area here. Okay, there's some area here, right, which you have to consider when you build a rectangle, right? So the rectangle or the brick wall equivalent noise bandwidth or filter bandwidth is pi over 2 times the pole frequency. Okay? All right? So this is the so-called equivalent bandwidth. All right? So we will use this a lot. All right? When we have any single pole system, all right, and we're going to find out what is the noise power, we will need to know what is the equivalent noise bandwidth to apply. Right? Because we don't want to do this integration every time. Okay? All right? So we will say, okay, so if I tell you you have a single pole amplifier with a pole frequency of 1 kilohertz, all right, and then calculate what is the output noise power if a white noise input source is applied, you should be able to do it with your eyes closed. All right? 1 kilohertz multiplied by pi over 2 to get my equivalent noise bandwidth, and that's my brick wall already. Okay? All right? So this you should also have seen before, right? I think Cedra and Smith has this, I think. Either Cedra or Smith or Gray and Meyer, right? They talk about this. Okay? All right? Okay, right, so this is what we call, right? So the fx is defined to be the equivalent noise bandwidth, okay? So fx is pi over 2 times your pole frequency of f0, or 1.57 times, okay? Right? So you can apply the same reasoning. That means if I don't have a single pole system, I have a 2-pole system. That means that there's a fp square, omega p square, right? And the thing is dropping faster. If I have 2 pole, how fast is the body plot dropping? Minus 40 dB per decade, right? So it's sharper coming down. Okay? Therefore, you can see that the equivalent rectangle bandwidth is smaller. Right? Smaller because the area under the dropping part is less. Okay? So instead of 1.57, it drops to 1.11. Okay? If I have a 3-pole there, okay, the rectangular bandwidth is very close to the pole frequency already. Okay? All this logically makes sense, okay? So you see the electrical engineer always very looking for a shortcut now. Looking for a shortcut. Right? So with this equivalent noise bandwidth, I can cover single pole, 2 pole, 3 pole, right? I got formulas there to use already. Right? You can calculate even more, but I think no need to calculate anymore. If you go for 4th order, 5th order, you might as well just use the pole frequency. Okay? Okay, so this is example, right? Example. Okay? So I input a noise signal to an amplifier with a given A of S, transfer function of this amplifier. And then find what is the output noise RMS, okay? Above 1 Hertz. Okay? So here is, what do I have here? Okay, so this is the noise, input noise, right? Input noise spectrum. Okay? It has two parts. This is the what? The flicker, 1 over F noise part. This is the white, the one noise part. Okay? Okay? And then, what is this? This is the transfer function, right? This is the transfer function of my amplifier. Okay? So this transfer function is quite interesting. Okay? Gain of 1 or 0 dB from DC all the way to 1 kilohertz. Okay? Then what happens here? There's a, looks like there's a 0. It's a 0, right? So 0, transfer function goes up. What happens here? There's a pole, okay, which cancels the 0, so it becomes flat. And then here you hit another pole, which causes it to come down at minus 20 dB per decade. Okay, so this is the amplifier with 1 0 and 2 pole. Okay, 1 0 and 2 pole, right? Okay. So now what happens if I apply this noise input into this kind of a filter, or this op-amp A of S? What will I get? Well, from here to here, the op-amp side do nothing, right? Gain of 1. Okay, so I just take this, follow. Okay, right? And then more than 1 kilohertz, the op-amp will start amplifying my noise. So my noise will go up. Then the op-amp will stay at a high gain, and then after that drop. Okay? So this is the noise output that I will see. Okay? Right? So now we can calculate what is the power of the noise, all right, from 100. Wait, Okay, so we can calculate from 100 to 1000 hertz. Right? That means this is 100 to 1000 hertz. Okay? This part here, right? 100 to 1000. This is, okay? Right? Okay? Basically here the magnitude is 20, right? So I take 20 square. And then from 100 to 1000. Then I can calculate what is the noise power. Okay? It's this value. And then we say, okay, what happens from 1K to 10K is from here to here. Calculate this. Okay? Right, here is going up by F. So power is F square. Okay? So you can calculate here. And then calculate the power from 10K, which is here. All right? To infinity. Okay? All right? That means you need to go from here all the way. Okay? So it looks like our So if you just chop it off, right? You just chop it off, it looks like our standard single pole system, right? Okay, if you just look from here onwards, flat, come down. Okay, so it looks like our single pole system. That's why we will use the equivalent noise bandwidth. Equivalent noise bandwidth that we calculated. Okay? And then to find a total noise, we just add up all the noise we calculated. Right? All the different bands, right? Okay? And we get, so the RMS noise is actually 77.5 microvolts. Okay? So you see people writing like this, right? Microvolt RMS, that means this is the RMS value of the noise. Okay? So this is not, it's simple mathematics, it's not rocket science. You don't need to have advanced calculus to do this, okay? Alright? Okay, what are some of the units that we define noise in, okay? This one important to understand because you'll come across this very, very often in double E, okay? What is the dBm? Okay? What is the dBV? What is the dBc? Alright? Okay? So what is dBm? dBm is the noise power normalized or relative to a power of 1 milliwatt. Okay? Right? So if something has a noise power of 0 dBm, it means that the actual power is 1 milliwatt. Okay? Right? What is dBV? dBV is the voltage, okay, relative to a given voltage level. Okay, so here I think there's some flexibility. People can define what is their reference voltage level. Is it 1 millivolt? Is it 1 microvolt? Is it 1 volt? Whatever. You need to know. If someone tell you, okay, this signal has a value of 10 dBV, right? First question you should ask is, okay, what is your reference? You must tell me the reference so I can map it back to the actual voltage. Okay? Okay, and then dBc is the reference is the power of the carrier. So C stands for the carrier. Okay? Alright? So this is very useful because in telecommunications, in a lot of times you have a signal that is sitting on a carrier. Whether it's the amplitude modulation, FM, whatever, you have a signal that's sitting on a carrier. So you want to know what is the power of this signal relative to the carrier. That's why I say dBc, okay? Alright? So I think this is given homework also, right? Something given homework. Oh, sorry. Will be given in the coming homework. Okay, will be given in the coming homework number 5. Okay, homework number 5 is coming, right? Okay, so first thing is, first part, what is the RMS voltage if I apply a 0 dBm signal, okay, reference to a 50 ohm resistor. Okay, so two things here. First note to note is the power of the signal is given in dBm. All right, so you automatically know that the reference is 1 milliwatt. Okay, that's how you map the dBm to a real power. Okay, and then how do you find the RMS voltage? You know that the power equals to what? V squared over R, right? Right, so if you know the power, you need to know the R to find what's the V squared. Okay? That's how you do the mapping. Okay? That's why you need to know what is R. So they'll tell you the R here is 50 ohm. Okay? So, first step, map the power in dBm to the RMS V square, which is So V square is P equals to V squared over R. So V is square root of RP lah. Okay. So R is 50 ohm. You know the power is 1 milliwatt because 0 dBm is 1 milliwatt. Take the square root. This is RMS. Okay. 223.6 millivolt. Okay. Okay. Second part. What is the power in dBm of a noise with 1 millivolt RMS? So now I give you the noise RMS voltage. I ask you for what is the power in dBm. Okay? So straight away you just apply the formula. Okay? Because here you know that we just work out here, right? We just work out. There's actually two steps, but here because you already work out the first step. Okay? So the first step will tell you what is the equivalent RMS voltage, right, for 1 milliwatt, right, is this, right? So therefore, if you take now I want to find out what is the dBm for 1 millivolt, so I did 1 millivolt divided by 0.2236 here, take the log and times 20, okay? That will give me the dBm, value, okay? You don't believe, you can go and work it out. Longer step is also okay. Okay? That means you just take 1 millivolt, okay, RMS, that means the noise power is what? 1 millivolt square, right? That's the noise power, right? I take 1 millivolt square, the noise power, and then I go and divide by R, right, to find what is the actual power in watts, right? And then go and find out what is the ratio of that power divided by 1 milliwatt. Okay? Then I can find dBm. You should get the same answer. Okay? Okay. So if you, so either way, you need to know what is the R value. Okay? You need to know what's the R value. Okay? Okay, then they ask you again, what is the maximum signal to noise ratio? Or if the SNR is 30 dB, what is the maximum signal strength in VRMS? Okay? So here, 30 dB, right? 30 dB. Okay? Yeah, so you ask you what is the signal power, all right? What is the signal power, all right, when it's 30 dB? So 30 dB SNR is what? Signal power divided by noise power, right? And if you want to express it in dB, times 10. Okay? All right? So SNR in terms of power dB is always 10 log. 10 log signal power divided by noise power. Okay? Right? So from here, okay, you can find out what is the because here, okay, part 2, part 2 you have the noise power here. Okay? So you have SNR, and you need to know what's the ratio of the signal power to the noise power. So here you calculate what was the noise power already, 46 minus 47 approximately. So from here you can calculate this was the signal power. All right? And then you can convert this signal power into the voltage equivalent. Okay? All right? Okay, so for all these things you need to combine, you know how to switch from dB into a real power or real voltage, right? And just do the switching left and right. Okay? Okay, so this reminds me, somebody asked a question, right? And this guy asked a question about the homework, about the formula to use. How come you cannot, he asked about the what? Yeah, the SNR. You know, the homework, there's a question on what is the how much oversampling you need to apply, right, to achieve the improvement, right? So there's a formula given in slide, don't know what lah. Okay, so there's two slides seem to have one slide give you the right answer. The other slide, if you use the formula, the 6.02b 1.76 plus 6.02b and then minus 5.2 whatever, right? If you apply b equals 2 into that formula, give you a different answer. Okay, so I gave the answer because it's important to understand the answer. Okay, so when we derive the SNR number, right? Okay, for the ADC, right? We derive it first. We derive the non-dB value first. Okay, which is basically a ratio or expression, and then from there we derive the dB SNR equals something, and then SNR dB equals something. Okay, so when you go from the SNR part to the SNR dB part, there was an important assumption. Okay, and what was the assumption? The assumption was that there's a term in the SNR expression of 2b minus 1. Right, it's 2b minus 1 square, right? Okay, when you did the derivation of the dB, there was an important assumption that 2b minus 1 is very much greater than 1, or 2b is very much greater than 1. Okay, so you just drop the 1 and just use the 2b, 2b. Okay, but when b equals to 1, that assumption is not true anymore, right? Because again, 2b is 2, right? 2 minus 1 is 2 and 1 are very close already. Okay, so that's the reason why in the other slide you cannot just use the formula directly. Okay, who asked the question? Right, so you understand the answer, right? Okay, so if you don't use the dB expression, just use the real expression, is correct. Okay, okay, another example. Okay, now, let's say I tell you the measured noise, the RMS voltage of the measured noise, okay, and ask you to find out what is the noise value in dBV, okay, all right, and I tell you, okay, I also tell you that the reference is 2 volt RMS, so this is very important part, right? So dBV, you need to know what is the reference. Okay, so 0 dBV means a 2 volt RMS signal. Okay, so now that I know the reference, I can do it very quickly, right? Is the noise, the dBV is whatever is my measured noise, 1 microvolt RMS, divided by my reference. My reference is 2 volt. Okay, I get minus 126 dBV. Okay, all right. So dB is always a ratio. Okay, so dB is always a ratio, right? So you need to know what's on the top, what's at the bottom. Okay. Okay, so that was for dBV. Now what about dBc? Okay, so now if you know that the carrier signal is 0.5 volt RMS, okay, and the noise is minus 60 dB, calculate what is the RMS noise level. Okay, so this is the equation again. 20 log. Okay, so important, dB, when you do the voltage to current is 20 log. 20 log something. Okay, when you do power is 10 log. Okay, don't mix it up. Okay, all right, don't mix it up. Power always 10 log. Okay, voltage current always 20 log. Okay. Okay, so here, because we're going to find out voltage RMS noise value, 20 log, okay, this is my unknown, my reference is 0.5, and I know it's equal to minus 60, I just work out, just plug in the values, I get the RMS noise is 0.5 millivolt, okay? So all these questions, once you know what is the right equation to use, is very simple, right? The calculation is not complicated, right? Either you take log or you take anti-log. Okay? Okay. So now what do we have here? Okay? Now things start to get interesting. Okay? So inside this box is your real circuit. It's your real circuit. Could be op-amp, could be anything. Okay? So in this real circuit, there are many different noise sources. Current noise, voltage noise, whatever, right? Okay? And then for this circuit, I apply an input. Okay? And I model the input with a voltage source input together with some source resistance. Okay? And then here is the output. Okay? Right? So, and I know that this is the transfer function, right? Output to this input, the input at my circuit input is a transfer function A of V. Okay? Right? Now, if I want to find out what is the transfer function from my output to my voltage source input, okay, I have to go through one more divider, right? Because now I have a source resistance and this has a input impedance. So it's like a divider. Okay, a divider. So output relative to this input, okay, there's this voltage divider, right? Input impedance Zin divided by Rs per Zin times AV. Okay, right? Now, why is this important? Because every signal source has to come from somewhere, and this somewhere will have some finite source resistance. Okay, every circuit has got some source impedance or whatever. Okay, all right. So the only thing that has got zero source impedance or source resistance is what? Is your SPICE voltage source. Okay, your SPICE voltage source has got zero source resistance. Okay, all right. Okay. So your SPICE circuit source is ideal. It's what I call ideal, Voltage source ideal, current source ideal, right? But your real circuit has got some properties. Okay, source resistance or source impedance is not zero. Your real current source, the output resistance, output impedance is not infinite. Okay, so this is the thing, So it's important to understand all this. Okay. Okay. So now, how do we look at this real circuit with all the currents and noise source inside here? Okay, so for analysis, what we like to do is, okay, to make our life simple, what we say is, okay, can we take all this noise source inside this circuit and just shift it out to here? Okay, so that I will treat this circuit now as noiseless, all right, and I'll model all the noise that was here as an equivalent voltage noise source and the equivalent current noise source. Okay, all right. That makes our life very easy, So this used to be a very noisy circuit. Now I can partition it to a noiseless part and then some noise at the input. Okay. So that's why we refer this noise as the input referred noise. Okay. Now, why is this useful? Why is this useful? Well, one thing it will tell me is that how much input I need to put in, right, to get some meaningful output coming out. Right? So because this circuit is noisy, it will have an equivalent input noise. Right? So if my real input is too small, okay, I can't see anything at the output because the output will be dominated by all the circuit noise. Okay, right? So this is very useful because it will tell us, okay, what kind of signal this circuit can process. Right? Okay, because that means if you give the input signal too small and the circuit noise is dominant, you will get all noise at the output. Right? You get nothing. Okay, right? Okay, right? So this is more some mathematics, right? How we can map all these equivalent noise sources. Okay, right? So here, remember, we map all the noise into here, into equivalent noise voltage, equivalent noise current. Okay, all right. And then once we do this, right, we can find out what is the actual output noise, right? Okay. So one way to do this is that we take all this noise inside here, all the noise sources, we calculate what is the output noise, okay, right, and then we map it back to the input, right, by dividing by the transfer function. Okay? Okay, let's see what else we can do. Okay, signal to noise ratio and noise figure. Okay, this is the other thing that's so signal to noise ratio, SNR, you encountered before in the lecture 7, right? That was when we used it to describe the ADC or the DAC, and that one actually, okay, we actually misused the noise definition. Okay, actually we were using the quantization error. Okay, we call it a quantization noise. Okay, for our analysis, right? But here now is the real signal to noise ratio, SNR. Okay, because now this P of n here, so SNR defined to be ratio of signal power to noise power. Okay. And this noise power is the real noise power now, okay? Whether it's the flicker noise power or white thermal noise power, this is the real noise power, okay? So either you take the 10 log of the power ratio, or you can take 20 log of the RMS voltage, okay? So here you can see where the 10 becomes 20, all right? Because the noise power is V square, V RMS square. Okay, right? So you know, I can take the square term out and then multiply by here become 20. Okay, that's why SNR in dB is 20 log voltage RMS ratio, or 10 log voltage squared ratio, or 10 log power ratio. Okay? Okay, that's SNR. Now the other metric or term that we use to describe noise is of a circuit, okay, is what we call the noise figure. Right? What is the noise figure? Okay? So the noise figure basically tells you how much the noise has increased going through your circuit. Okay? Okay, so first we will define the noise factor. Okay? That means the total is the ratio of total output noise power divided by output noise power due to the input only. Okay, that means here is this total is input plus your circuit. Plus your circuit. Okay? This one is from your input source only. Okay? So obviously your circuit will add some noise, right? Because your circuit is real. It's got a noisy component. You will add some noise. So this will be bigger than this. Okay? Right? This can never be equal or smaller than this. Okay? Right? And the noise figure is defined to be 10 log of this ratio. Okay? So noise figure is always given in dB. Okay? Noise figure is always given in dB. Right? And to map noise figure to the ratio, which we call noise factor, you need to use this equation. Okay? Right? Alright, so the noise figure in dB is 10 log this ratio. What is this ratio? What is the total available output noise power is, let's see here. Okay, it is you take the transfer function, okay, multiplied by the total input noise. So here is the total input noise, okay? Then you divide by the different transfer function from your source, okay? All right? And then, because these two noise is related, it works out to like this, okay? That means here the total is the source plus the equivalent input referred noise of your whole or your circuit, right? The voltage part, and then the current part, okay? Multiplied by your source resistance, okay? Alternatively, you can derive it this way, and then you will find out that it can also be expressed as a ratio of SNR of the input divided by SNR of the output, okay? So obviously the SNR of your input, it must be higher than SNR of your output. Okay? All right? Because your circuit is injecting noise. Okay? So the noise figure will always be, the noise factor will always be greater than 1, which means that the noise figure in dB will always be greater than 0 dB. Okay, it's not possible to have a noise figure which is minus some dB. Okay, right? If you have something at minus dB, it means that your circuit somehow is is able to generate negative noise. Okay. Okay, I think this is a good place to stop, right, for our break. All right. After the break, we'll talk about the different noise sources and models from the actual circuits. Okay? So let's come back at 7:50. Is that enough time? What do you normally do for this break? Oh, my interest. What do you normally do? Apart from going to the toilet, taking a drink, what else do you normally do during this break time? Sleep. Okay, so 7:50. If you need more time, you have to explain to me, why you need more time. You want to go there, have a good meal or whatever. Okay, 7:50. See you at 7:50. Okay, is everybody back ready from the break? Okay, maybe you ask you a simple question. Which is your favorite food store on campus? Which is your favorite food store on campus? The food place that you eat the most often. Anybody? Where do you normally go and eat? Engine canteen? Is it? Most of you eat at engine canteen, is it? What is the best store there? What is the best store? There's a Western store, is it? Western, is it? Anything else? Anything else? There's also a Malay store there, right? Okay, I'll try one of these days. Okay. Any questions regarding the first part of the noise? Okay. If not, let's continue. Where did we stop? You want to stop? Okay. So here I think we see from a real circuit, okay, where in the circuit is noise being produced. Okay. So in a lot of the circuit elements we use, there is noise. Okay, there is noise, and we'll see that. Now there are other parts of the circuit that will produce. Actually, will produce errors, will produce errors, which we sometimes will call noise. Okay, so that is a bit of a flexible use of the term noise. Okay, this one we already encountered in the lecture 7, the data converter, ADC-DAC, the quantization noise or the error. Then we'll see that some for MOS transistors, you know the MOS transistor has a channel, right? Has a channel. So it means that when the channel is on, there's charge under the channel. Okay? So what happens when I turn the channel off? Right? The MOS transistor, right? I can turn it on, create a channel, then I can turn it off. Yeah? For NMOS, I just put the gate to ground now, right? I turn off the channel. What happens to all the charge? Okay, the charge doesn't just disappear, okay? Okay, the charge has got to go somewhere, okay? So the charge, when you turn off the MOS transistor, turn on a channel, the charge is injected out. Okay, so this is what we call charge injection. And obviously, you inject charge somewhere, it could cause an error. Another type of error or noise is called clock feed through. Anybody know what is this? What is clock feed through? Okay, so in your circuit, in some circuits you use a clock, right? You use a clock. So the clock is a square wave, right? Okay. So when you apply a clock to, let's say, an MOS device, what will happen? You turn the gate on and off, right? Okay. Let's say you use the MOS as a switch, okay, and you apply a clock as the gate signal. Then the gate input will be up and down. Okay. Your real MOS has a gate to source, gate to drain overlap capacitance. Okay. So when your gate is switching, okay, the drain and source may have some other capacitance connected. Then you have a capacitor divider. Okay. So the gate side is up and down. So depending on the capacitor divider, the sum of the source and drain, you also see some disturbance there. Okay, this is what I call clock feed through. Okay, and then of course there could be crosstalk and interference. Means that the crosstalk could mean you have two metal lines in a circuit. All right, and if they are too close together, and this line is moving with a clock maybe, right? If they're too close, there's some capacitance that connect the two, then some of this voltage change will inject into here. Okay. Okay. And DC offsets. So some people call DC offset a noise. Obviously, DC offset is not really a noise, okay. Okay. So the first thing we want to talk about is the common element we use, a resistor. Okay. So does a resistor have noise? What do you think? Does resistor have a noise? Obviously, you look at this slide. This slide there got noise now. Okay. But why do you think resistor has noise? Oh. Okay. So actually, it comes down to the this term thermal or Johnson noise. Okay. So the electron or the carrier, how does it go through a resistor? Is it just going in a straight line? Okay, because you have resistor got lattice atom all that, right? So actually it's collision, ding dong, and go on. Okay. So it's going across because there's a electric field that pull the thing across, but because inside there's lattice atom, there's obstruction. Okay, that's why there's resistance. Okay, so the movement of the carrier, whether it's the electron or the hole, actually, right, is a random motion. Okay, and this random motion is what gives rise to noise. Okay, right. So here is the equivalent noise model or resistor. Hopefully, this is not the first time you saw. Normally, you just draw the resistor like this, right? Okay, but actually, because of the noise, you model it with a noise source. Okay, so what is the NSD, or the noise spectral density of a resistor noise, is 4 kTr. Okay, the voltage noise power of a resistor is 4 kTr, which means what? Is proportion. What is K? What constant is it? K is the Boltzmann constant, Boltzmann constant, right? What's the value? 1.38 times 10 to the minus 23. Okay, what's the unit? Okay, go and check yourself, okay? All right, okay? T is what? In what units? Okay, Kelvin, degrees Kelvin, absolute temperature, okay? Absolute temperature. And actually, the physics of this is quite easy to understand, because it's, the motion of the carrier is random due to, and it will be blocked by vibration of the lattice atom, right? So when the temperature increases, there's more vibration, there's more obstacle, okay? That's why the noise is increasing with absolute temperature. And then R, of course, is the resistance value, okay? So 4 kTr is what you need to remember. Okay, that is the resistive white noise spectral density. Okay, flat across all frequencies. All right. And then what we will do is, for our real circuit, we need to know what is the bandwidth. All right. Okay, because this resistor noise you apply to a circuit, there will be a finite bandwidth. Okay. All right. Oh, okay. So another way to model, instead of using a voltage noise source, you can also model using a current noise source. Okay, right? So they are equivalent, equivalent, because if you look at these two terminals here, okay, if I look at just these two terminals, okay, open circuit, I will see this noise, right? Here, if I use the current, I look into these two terminals, I will see IN square R, IN square times R squared. Okay? And because IN square, the current noise is defined to be 4 kT over R. If I multiply by R squared, I get back to 4 kTr. Okay, so it's equivalent. Okay? So it's like the two equivalent model, Thevenin equivalent and the Norton equivalent. Okay? Now, why do we have two different representations? Anybody want to guess? Why do we have two? Okay, simply because depending on the circuit that you're considering and how you want to analyze it, sometimes it's easier to use the noise model, the voltage noise model. Sometimes it's easier to use the current noise model. Okay? Right? So keep in mind, so if you choose the right model to use, it makes your analysis simpler. Right? If you use the wrong one, you can still get the right answer. It's just that analysis may be a bit more complicated. That's all. Okay? And you'll see that in homework number 5. Okay? Okay. Now, this is another important noise concept, called the KT over C noise. Okay? So if you are doing research or doing coursework, whatever, in analog circuit, you will definitely come across this term KT over C. All right? So it's good to understand what is this KT over C noise. Okay? So consider that we have this circuit. Okay, we have a resistor followed by a capacitor. Okay, this simple RC circuit. Okay? Now, we know that the resistor has a noise voltage. Okay, so we can redraw like this. And then we can say, okay, if like this, what is the noise that appears here in this RC circuit? What is the noise that appears across the capacitor? Okay? Now, why is this useful? Simply because in a lot of circuits, we'll use the capacitor as a sampling element. Okay? Alright? And we use the switch to say open or close the switch. Alright? Turn the switch on or off. Okay? I turn the switch on, I connect the capacitor to some voltage source, and then when I turn the switch off, I want to sample the value on the capacitor. Okay? So this is similar to this except that this R is the resistance of the switch. Okay? So in this case, we want to find out, okay, what is the noise that gets sampled on the capacitor or appear across the capacitor? Okay? So we can do our analysis. Okay, we know that the noise voltage power spectral density is 4 kTr, right? From previously. Okay? We know that this is RC, so RC we can derive the transfer function. Right? Correct, huh? This time you must know, okay? How to derive the transfer function of this circuit, right? What is this voltage? What is the transfer function of this voltage compared to the source? Okay, so it's just a simple impedance divider, 1 over SC divided by R plus 1 over SC. Okay, simplified. In J omega, you get this term. Okay, and then this output noise is simply this voltage noise power spectral density multiplied by the square of the transfer function. All right, integrate from 0 to infinity. Okay, but you know that this thing basically has this basically is a low pass. Okay, it's a low pass. Okay, it's a low pass. All right. Okay. So from a frequency point of view, you can see that, right? Basically, is this 4 kT over R is wide, right? It's flat across. But then because this RC has a single pole, right? Single pole here. So you have an equivalent noise bandwidth. Okay. So you do the integration, you find that this noise power across the capacitor is kT over C. Okay? Okay? So the sampled noise power across here is kT over C. This is the output V RMS square. Okay? kT over C. Okay? So this you get from the pure mathematics. You just integrate. Get the transfer function, square, do the integration. Okay? 0 to infinity. Okay, you get kT over C. You can do the same thing using our trick of finding the equivalent noise bandwidth. Okay, right? Okay. So for single pole, okay, omega p is 1 over RC, right? Omega p 1 over RC, right? Okay, and then frequency is 2 pi. No, omega is 2 pi. Omega p is 2 pi f p. Okay? So fp is omega p divided by 2 pi. Okay? Alright? So, it means the equivalent f0 or fp is 1 over 2 pi rc. Okay? And then from the previous slide, we derived what is the equivalent noise bandwidth of this single pole is pi over 2 times the fp or f0. Okay? So we get this. Right? So this is the equivalent noise bandwidth. I just take my 4 kT over R multiplied by my 1 over 4 RC, I get kT over C. Okay, so it's same information, okay? Alright? Okay, so this term is interesting, you see. Even though this is the noise power due to the resistor, okay? This is the noise power due to the noise source of the resistor, right? Okay, because we assume the capacitor is ideal, so the capacitor got no noise. Okay? So the noise power due to the resistor, but the actual expression don't have R. Okay, what happened? Why? Good question to ask, right? Why? The noise actually is coming from the resistor, 4 kTr. Then now, because I go through this RC network, I look at the output noise, power, R disappear. What happened? Is it magic? Anybody know the answer? Actually, the answer is here. Answer is here. Right? Because to calculate the noise power, you need to know what is the frequency bandwidth. You see? And the frequency bandwidth is defined using R. Because this is RC. Right? Okay? So the R also appears in the frequency bandwidth part. Right? So when you multiply it, they cancel. Okay? That's why the R disappear. Okay? Okay, so important to understand this. The KT over C noise is due to the noise of the resistor. Okay? It's not due to the noise of the capacitor, okay? Because the capacitor is assumed to be noiseless. Okay? Okay. So apart from resistor, how about diodes? Diodes. PN junction diodes. Okay? The PN junction diode, okay, also has got noise. Okay? Also has got noise. Right? So this is the equivalent model. This is the equivalent model of a diode. That means if you say, I want to model the diode by its equivalent resistance, RD, all right? And there will be a noise current of this diode. Okay? So this is real. If you go and bias up a diode, right, with current and with a voltage source, right? Okay, voltage source, resistor, go through a diode, and you measure the current, okay? You'll see that there's actually a bit of noise here. Okay? Right? So the actual noise, actual dark current is not straight, okay? It's not a simple DC current. There's actually movement. Okay? Alright? So this is the probability density of the noise current, okay? P of I is the probability density. Okay? This is a DC value, but there's some probability that is shifting around the DC value. Okay? So the noise spectral density of this diode current, okay, I square, is 2qID. 2q is electronic charge. ID is whatever is the DC bias value. Okay? And then you can and then the RMS is you just take the square root. Okay? No. This is the spectral density. This is the actual noise current output. Okay? You take the spectral density, multiply by the bandwidth. Okay? Now you can transform this. If you don't like to use a current, you can also transform this to equivalent voltage noise. Okay? Then you use the RD, okay? RD defined to be KT over QID. Okay? You can find the equivalent diode voltage noise spectral density, and the actual output power is multiplied by the bandwidth. Okay? Okay, so now we come to this element of the bipolar junction transistor, BJT. Okay? Are you familiar with BJT? Are you familiar with BJT? How does a BJT work? Is this still being taught in undergraduate, BJT? Huh? Okay, so this is one of the history of semiconductor, okay? So when semiconductor first started, BJT. Okay, actually, the Nobel Prize, I think, by the Bell Labs guy was for BJT. Okay, when they first demonstrated semiconductor, okay, was a big device, is a BJT. Okay, it's a bipolar junction transistor. Okay, and then I think all the way from the 50s to the 60s to the 70s, okay, BJT, the bipolar junction transistor, was the dominant transistor being used. Okay, and then what happened? Because electronics had to become bigger and more devices, okay, then the invention of the MOS transistor, the metal oxide semiconductor, FET, came up. Okay, and soon this one became dominant because it was easier to integrate, it was easier to build logic, CPU, everything, right? In digital circuits, the MOS became dominant. Okay, so much so that now, I think less and less people know about BJT, okay, and how the BJT actually works. Okay, so the quick lesson, MOS, very simple device actually, right? One gate, create a channel, and that's it. Okay, and then once you create a channel, the current just flow. Okay. So BJT, bipolar junction, two junctions, okay? Base emitter, forward bias, like a diode. Base collector, reverse bias, okay? So carrier is injected through the forward bias base emitter junction, all right? And part of the carriers diffuse through the base to reach the collector, and then they're collected there, okay? So it's a two junction, one junction for the injection, and then diffusion to the other junction. Okay, for this one, we will not go through in detail, okay? So for this bipolar, there are a few different noise sources, okay? From the base and the collector current, there's what we call a short noise, okay? A short noise, right? And then the base current also got a flicker noise part, okay? And the reason is because there's trapping and releasing of carriers, okay, of energy states. Okay, this is some device physics. This is caused by defects in the material. And then we also have white noise in the base because the base has got some resistance, all right? So this resistance got the white noise, okay? Okay, so this is the different sources. Okay, so then we have to start to model this now, okay, of the bipolar junction. So this is the NPN, NPN bipolar junction transistor, collector, base, emitter. Okay, so you have short noise here, okay, 1/, noise here, equivalent noise currents, and then here is the base resistance 4 kTR noise source. Okay, so here already you have 3 noise sources, and then we have a noise source here from the emitter to the collector. Okay, so now with this 1, 2, 3, 4 noise source, okay, 4 noise source, we want to simplify to only 2. 1 noise voltage at the base, and then 1 noise current from the base to the emitter. Okay, so we need to combine all these noise sources into 2 equivalent noise source. 1 voltage noise, 1 current noise. Okay? So for the voltage side, the base we can just take this 4 kTRB here. Okay? Then, what do we need to do? We need to transform all these noise current to the output noise current, all right, and then take the inverse transfer function from output current back to the input, base input. Okay? So you know transistor, right? Input times the transconductance will give you the output current. Right? GM. Transconductance is a GM. Okay? So whether for MOS or bipolar is the same thing. There's a GM. GM is the ratio of the, for the MOS is the drain current divided by the gate to source input voltage. Okay? For the bipolar is the collector current divided by the base to emitter voltage. Okay? Okay? So we do the mapping of all these things, okay? We can get the equivalent noise voltage and the equivalent noise current. Okay? So these two I think is quite, yeah. So these two, this one, right? You just add these two together. Okay? Add these two together. And then you need to transform, this is the current here, all right? This is the collector current. You can transform, you can map it to an equivalent base current because you know that the base current collector current ratio is defined by beta. Okay, so that's the transfer function. Okay. And to make our life more complicated, you know this beta is also frequency dependent. Okay. Okay. So now we come to our MOS transistor. Okay? And where is the noise for this MOS transistor? Okay, we already mentioned the MOS transistor has a channel, so there's thermal noise in the channel resistance. Okay? There's also flicker noise in the channel. Okay? That's because of the gate interface to the substrate. Okay? There's also induced gate noise, and then your drain side, your source side, your gate side, there's also some resistance there. Okay, so all these things are all, in the real component, you cannot run away from resistance. Okay, so when you have resistance, you have thermal noise. Okay, so when you use a polysilicon gate, the polysilicon itself, even though it's highly doped, there's still resistance there. Okay? And then you have your source drain and your source bulk and drain bulk. There are junctions there. Okay? There are junctions there, so there will be some junction leakage current. This will cause short noise. And then your substrate or your body will also have some resistance, and this will create some thermal noise. Okay, so there's actually, even though it's a simple device, there's many noise sources there. All right? So what we will define is this. We will say that, okay, my MOS transistor has a drain current, and this drain current will have thermal noise, and we will call it 4 kT conductance of the channel, or 4 kT gamma times the GM. Okay? All right? So we take all these and we simplify to say, okay, there is a drain current. Okay? There's a drain current noise, okay, of this value. And then this gamma value will depend on whether we're operating this MOS transistor in what region. Okay? Are we operating in triode? Triode means what? Channel all the way from source to drain. Okay? Fully turn on. Okay? Like a switch, you turn on. The channel exists from source all the way to drain. This is what I call a triode operating region. Okay? Or if you are in saturated mode, okay, you can either be in strong inversion or weak inversion. Okay, depending on how much overdrive you apply to the gate to source. Okay? So this gamma value is changing, okay, depending on which operating region you are. Okay? this is basically because the real transistor is quite complicated. Okay, so we're going to try and simplify the modeling a bit. Okay. Okay. So the flicker. So we talk about here, right? This was the equivalent noise current MOS, the IND square, the noise in the drain, and then there's a voltage noise source in the gate. Okay, and this is the so-called flicker noise. Okay, and this is basically due to the fact that at the interface of the gate with the substrate to form the channel, there's an interface. Okay, this is interface of two different material. Okay, the gate is what material? Oxide, right? It's oxide. Okay, it's oxide. Okay, I'll just say, okay, this is historical, okay? For a long time it was oxide, but now the new transistors are different kind of material, okay? But let's just stick to oxide. MOS is metal oxide semiconductor, okay? All right? So because it's oxide and silicon, there's an interface. So this interface, sometimes there's some defect there, right? And this defect will cause traps, right? So these traps may affect the movement of the carrier. So, and this traps will trap some carriers, and so it looks like a flicker effect. Okay, so some carriers when it's moving will get absorbed by the trap. Okay. Okay, so for the MOS transistor, there's quite a lot of different noise, but we simplify to only two components. Okay, like the bipolar also simplify, right? One voltage noise, one current noise. Okay, voltage noise is 1 over F. K is some constant, 1 over F. And the current noise we can also refer back as a voltage noise by using the transconductance again. Okay? Okay, so repeat again. The MOS from so many noise sources, first is simplified to two. Okay? Gate voltage noise, drain current noise. And then this drain current noise can also be simplified back to the input, right? By taking the transconductance. Okay? So remember, this was like this, right? 4 kT gamma GM, right? And then to refer back to voltage, I divide by GM square, right? Okay, so I take this, divide by GM square, I will get 4 kT gamma divided by GM. Okay, right? Okay, so important thing to note is that how to refer this, how to refer this back to the voltage input, right? Through the transconductance GM. Okay. Okay, so at least for this is simpler than bipolar. Right? Bipolar got one voltage noise and one current. Okay, now MOS is just everything simplified to only one voltage. Okay. Okay, so this next slide basically says about what is some of the other noise, like the gate induced noise, okay, or gate noise current. Okay, so this is another level of noise modeling where you actually say, okay, now I have a gate induced noise, okay, but it's only important at high frequency, okay. So low frequency we just neglect it for the time being. Okay. Okay, so finally now we have our good friend, the op-amp. Okay, so we do the same thing for the op-amp, right? We say, okay, my op-amp core is noiseless, and I move all the noise from inside to the input side. Okay, that will simplify my analysis. Okay, so I will say that my op-amp core is noiseless, but I will have one voltage noise input model and two current noise at each of the inputs. Okay, all right. So this is how we model a real op-amp with noise. Okay. So if this is a MOS, normally what we do is we can ignore the two input noise sources. Okay. But if there's any question that comes out, they will tell you. I will tell you specifically, right, what to assume. Okay. Well, we already went. This is supposed to be a break time now. Okay. So how do we do the noise analysis and estimation? All right. So here is the procedure. Okay. Here is the SOP. SOP. You identify all the noise sources in the circuit. All right. Identify the noise sources. You replace the noise source with the noise model. Okay, at the noise equivalent circuit. Okay, we know resistor is 4 kT over R, voltage noise. Diode is I think a current noise or voltage noise. You choose which one you want. All right. Bipolar has got this one voltage and one current. MOS, you either use voltage and current or use voltage alone. Okay. Then you go and calculate what is the effect at the output of all these noise sources. Okay. So you find what's the total noise power at the output, and then you may want to convert the noise to voltage to current or whatever. Okay. After that, from the output, you calculate what is the equivalent input referred noise. Okay. How do you do that? You use the transfer function. Okay. Transfer function is output to input. So once you calculate what is the output noise, you divide by the transfer function, you can calculate what is the input equivalent noise. Okay. So this is basically is the important thing to know and to understand. Okay. Okay. So this example, let's say you have a cascode amplifier, which you will cover in part 1. Okay. Cascode amplifier. Okay. Very simple, nothing complicated. Cascode amplifier means that you have M1, you apply the input to the gear M1. Okay, M2 is the cascode device, we need to bias up. And then L is the load, the output is taken from here. Okay? Alright? So now we know, right? This burger R has a noise source. These two MOS also got noise. Okay? So we just take our noise procedure, all right, and apply it to this circuit. Okay, right? So for these two guys, right, we just take the equivalent input noise voltage. Is 8 kT divided by 3 GM. Okay, where did we get this? If you go back here, not this one. We got this, right? 4 kT 1 over GM. This is for 1. This is for 1, right? Okay. So if I have 2 become 8, right? Yeah. This is the equivalent noise from these two guys. Okay. And then this one is 4 kTr. Okay. All right. Okay. See, so now we put here, right? This M1 got this noise voltage, M2 got this noise voltage, RL got this noise voltage here. Okay. So now, how to calculate what is the noise at the output due to these three sources? We will use the principle of superposition. What is the principle of superposition? 1 by 1. Okay, 1 by 1. Okay? What is the output noise power due to noise source 1? Then what is the output power due to noise source 2? What's the output power due to noise source 3? Then we use our uncorrelated assumption, right, to add these 3 noise power together. Okay, that is a simple analysis. Okay? So you can go and find out, 1 by 1, right? So first one here now is that we just take this one. Okay, what is the output here due to this guy? And then we calculate what is the output due to this guy. Okay? So you need to work out what is the transfer function. So the tricky part is you need to work out a transfer function from the noise source to the output. Okay, that's the only complicated part. Okay, the reasoning is a very simple one. Right? And the resistor is quite straightforward. You just add, because it appears the output. Okay, it appears the output, so you just add it in. Right? So total output noise power, add 1, 2, 3. You get all this. Alright, and then what you'll find is that actually this one is dominant. Okay? This GM1 times RL is a big number, so normally this term is dominant. Okay? And then you have the output, then finally you just refer back to the input. Just divide by the gain, magnitude gain square. Okay? Alright? Okay, and then you can see, right? You can see that you have one term that's due to the noise that's due to this RL. Okay? And then you have another term which is controlled by the input transistor, M1. Okay? You assume this one is small. Okay? Okay, so this was the analysis, quick and dirty, okay? Quick and dirty. Okay, that means you need to know how to write out the transfer function, okay? This is analysis. If you don't use the quick and dirty way, you use the full small signal model. Okay? You all know what is small signal model, right? What is small signal model? Anybody? Okay, this is the part about electronics that you must try to understand. What is small signal model and what is the large signal model? What's the difference? Okay? Okay, so this is interesting. I don't want to spend too much time on this, but you know that all your devices, your MOS devices, everything, is non-linear, right? Right? It's a non-linear device, right? If you plot ID over VGS square, VGS is a square term, right? It's a quadratic term. Okay? Bipolar is exponential term. Okay? So the device from a large signal point of view is non-linear. Okay? But when you want to try to do something useful, all right, we want to have a linear circuit. So how do we use a non-linear device to do linear operations? We have to select an operating point. Okay? And then we apply small signal to this operating point. That's why the term is small signal. Okay? So when you apply small signal to a defined bias operating point, you will get a small signal equivalent. So this is meaning of small signal model. Okay? Alright? So here is the small signal model of MOS, right? Gate, source, this is the drain. Okay, sorry. This is the M1, okay? Gate, source, drain. Okay? Alright? Actually, there's a capacitance here, but I mean, we will not consider, we just say this is treated as a relatively low frequency, so we just throw away the capacitance. There's also a gate to drain capacitance also we throw away because we say that, okay, that's only valid for high frequency part. Okay, then you have the GM current, output resistance. Okay, this is M1. This is the equivalent for M2. Okay, small signal for M2, right? M2 is what? So you say, okay, what is what now? So M2 source connected to M1 drain. Source M1 drain. Okay? M2 gate is grounded. Okay? Gate is grounded, and then drain connected to RL. Okay? Right? Okay? So this is the equivalent M2, and here's the RL. So this is a complete small signal model of that circuit. Okay? Which you want to analyze. Okay? Which you can analyze again. Now, once again, do the same thing. Okay? Find out what is the noise. So this is the noise due to the M1 noise voltage. Okay? Here, what appears here? Okay, do all the calculation, you get this. Okay, and then repeat for N2 now. Okay, now N2 appears at the gate. All right. Okay. Okay, so calculate again. What is N2? And then N3 appears here. Okay. So you calculate again. So same result. Okay, same result. Okay. So another example here. All right. This is our familiar inverting amplifier. Okay. Amplifier R1, R2, negative feedback. This inverting amplifier, right? Gain of this. What is the gain of this inverting amplifier? R2 over R1, right? Okay. R2 over R1. If you assume that this is ideal, okay. If it's not ideal, then you more complicated expression. Okay. Okay. So basically, you have this inverting amplifier. Okay, and we know that the noise spectral density, okay, is 8 nanovolt per square root hertz. Okay, and then, so this is the equivalent input noise voltage spectral density of your amplifier. Okay, so remember, this was the model for your op-amp. Remember? Right? We said that there was a voltage noise equivalent and 2 current noise. Okay, and most of the time with this MOS we just ignore the 2 current noise. Okay, that's why we just give the voltage noise of this op-amp. Okay? Right? And then we say, okay, we know that the unity gain bandwidth of this op-amp is 10 megahertz. What is the input and equivalent? What is the output and equivalent input noise RMS value? Okay? So now we draw the circuit with all the noise sources. This is the op-amp noise input voltage. And then we know that these two guys, resistor, got noise. Okay, got noise, right? And we choose now to draw the noise as a current. Now remember, for resistor we can either use voltage or current, right? So we choose to draw it as a current. Now why? Why? Okay, because it's very simple, because if it's a current, then very easy, right? To find out what is the output noise voltage, this current will just add to this current and go through here. Okay, very simple, right? If I draw as voltages, could be a bit more complicated to analyze. right? If I draw as the voltage, okay, let's say I draw this noise as a voltage here. Okay, maybe not so bad because here is next to the output, so I just use this voltage directly. Okay, how about here? If I draw this as a voltage, I need to consider voltage source here, how to change from a voltage here to the output. Okay, all right, but it can be done, and it should give you the same answer. Okay, if we do correctly, right? Okay, because they are supposed to be equivalent. Okay, but we do this for current because it's simpler, okay? All right. Okay, so you can see, right? You put the two noise current, you just add the two noise current power, multiply by R2 squared is what is happening at the output. Okay? All right? Okay? And then you have to be careful here. So to calculate noise, you need to know what is the bandwidth to consider, right? To use, right? So what is the right bandwidth to consider? You're given here that the unity gain bandwidth of the op-amp, unity gain, is 10 megahertz. All right? But this circuit is being used in a closed loop configuration. Okay? So actually the right bandwidth to use is what is the closed loop bandwidth of this circuit. Okay? This circuit in closed loop is definitely not unity gain. Okay? I think this is another thing that probably covered in part 1. Okay? Okay, but this circuit is used in closed loop. So actually, the actual bandwidth in this closed loop is actually the unity gain divided by 100 because your closed loop gain is 100. Okay? Okay, if you don't know, think about this, all right? And then you still can't understand, send me an email, I'll answer you. Okay? All right? Okay? Because the simple answer is this, the feedback from the output to this input here is not unity. Okay, it's not unity. All right? The feedback here, output to here, is going through this divider. Okay? Okay, anyway, so the closed loop factor is 100. So actually, it's, you need to divide by your 10 meg by 100. So you get actual closed loop bandwidth is 100 kilohertz. Okay? All right, so the noise power at the output, okay, due to the current sources, the noise current source is this, right? Add up the two noise power, okay, then the two noise current power multiplied by R2 squared because it appears at the output, right? I times R, right? I times R2, to get the output voltage square, and then I multiply by the equivalent bandwidth frequency, okay, which is my noise equivalent bandwidth, pi over 2 times whatever is the bandwidth, okay, right? So you get this, okay? It's the noise voltage square is about 162.1 microvolt square, okay? Okay, this is only one part, because we need to consider the noise current first, okay? These two guys. Now we're going to consider this guy. This is voltage now. Okay, so we draw the circuit again, superposition, throw out the noise current, now only consider this voltage here, okay? What is the output due to this guy? Okay, this is a straightforward non-inverting amplifier, right? Okay, so here we assume this gain is very large, so this guy will appear here, okay? This will create a current. This current will flow through R2 to give the output. Okay? So the non-inverting amplifier transfer function is 1 plus R2 divided by R1, okay? Because here is a V, Vs divided by R1 is the current, And this current multiplied by R2 is output voltage. So this voltage is Vs plus whatever is this voltage drop here, okay? Right, then you multiply by the equivalent bandwidth again, you get this output noise power, okay? 320 microvolt square. And then we need to combine the two of them, square, find the RMS, you take the square root. Okay? Alright? And over here you'll find that actually it's dominated by this guy. Alright? See, this guy alone is 320. See? When you combine the current, only increased by 39. So it's dominated by the noise due to this guy. Okay? Then finally, if you want to find what is the equivalent input referred noise RMS, you take this, right, divide by the gain, okay, by the inverting amplifier gain, which is R2 divided by R1 square. So the equivalent input RMS noise power is 3.6 microvolt. Okay? So once again, it's important to understand the sequence, how to do this, right? Find out all the noise sources and what's the equivalent model. Okay, find out what's the output power, noise power due to each of these guys by superposition. Right? After that, refer back to the input using the transfer function. Okay, and then that's it. Okay? So the tricky part is finding the transfer function, right? And finding out what is the proper bandwidth to consider, okay? Right, you get these two things correct, you're okay already. Okay, so we talk about noise. Now, since noise is bad, because noise will degrade your signal, okay? So there are certain things you can do to try to minimize the noise or suppress the noise, okay? One, of course, is to optimize the operating condition. Okay, so you know some of this noise is due to, like the resistor, due to the value of resistor you choose. You choose a bigger value, the noise bigger. All right, so can you choose a smaller value or not? Okay, there's a trade-off, right? Okay, some of this noise, like the short noise, all that is proportional to bias current. Okay, all right. So you can choose the bias current. You want to have less short noise, maybe lower the current. Okay? Transistor, MOS transistor. Thermal noise is inversely proportional to GM, transconductance. Right? So you want to have lower noise, you need a bigger GM, which means that you need how to get a bigger GM? You need a bigger transistor or you need to have a higher current. Okay, so no free lunch, no free lunch, okay? Okay, you want a higher current, you burn more power. Okay, all right? Or maybe you say, okay, maybe since we know the noise is proportional to the bandwidth, okay, try to minimize the bandwidth. How to minimize bandwidth? Do filtering, okay? How about 1 over F noise? 1 over F noise, flicker noise, right? Most of the power is in the low frequency, near DC, right? Okay, what can we do? Right? We will see that there's something you can do, okay? And then, of course, there are things we already talked about, like oversampling, spread the noise out, right? Spread the quantized noise out, and then we filter, okay? And then finally, we also talk about this concept called spectral shaping, which is actually, we saw in delta sigma converter. You can actually shape the spectrum of the noise, right? To do the noise shaping, right? So that you push the noise out towards high frequency. Okay? So there are a lot of tricks that people have learned, engineers have learned all through the years. Okay, this is what I mentioned, operating condition, right? With 1 over GM, can you try to increase the GM or not? Okay? So bipolar, the noise depend on currents. Okay? Alright? Can you reduce the currents or maximize the beta? Okay? MOSFET, okay, once again, you want to cut down on noise, increase the transconductance. Okay? So MOSFET, you have another degree of freedom, because in MOSFET you can use it either in weak inversion or strong inversion. Okay, you all understand what is weak inversion, strong inversion? Okay. So in MOS, you want to form the channel, right? Okay, so you can form the channel either very strong or very weak. Okay, very strong means if I apply a very high gate to source voltage, okay, much higher than my threshold, all right, then I'll form, the higher this gate to source is, the stronger is my channel, all right? So if it's gate to source is very high, we call it strong inversion, okay? If the gate to source is very small relative to the threshold, okay, we call it weak inversion, right? Okay? Okay, so in the MOS, the GM is maximum at weak inversion, okay? So the weak inversion may produce better noise performance. Okay, then the noise, flicker noise, whatever F noise, is inversely proportional to the gate area, right? So you see the term, it is K divided by WLC ox, right? F. So if you make the gate area big, you will reduce the flicker noise. Okay, but of course there's some limitation. You cannot build a very huge transistor, right? Okay. Then also interestingly that for CMOS, because you have a PMOS and NMOS, in some technologies actually the PMOS may have a lower flicker noise than the NMOS. Okay. So if you need so in these kind of technologies, if that is true, then you want a low noise design, especially the input device. Maybe you want to choose the PMOS instead of NMOS. Okay? But once again, there's a trade-off, right? Because normally the mobility of the PMOS is lower than the NMOS. You all know why? The carrier mobility, the whole mobility is lower than the electron mobility. Okay? So a lot of trade-off here. Okay, so now you compare BJT with MOSFET. Actually, you don't have to compare because most of the design you use, you're designing using MOSFET. Okay, all right. So the state of affairs nowadays is that most design is done in MOS. All right, and the only place where we are still using bipolar is what? In MOS. Huh? Sorry? Yeah, it's when you want to design a band gap reference, okay, you use a bipolar because there is a bipolar available in MOS technology and it's called the substrate bipolar, the PNP. Right? The substrate of the CMOS is a P. Okay? All right? And then you have a P diffusion inside an N well. Okay, that's a P plus N minus substrate. That's the PNP. It's a parasitic transistor inside the technology. Okay? But that's the only bipolar that's available in bulk CMOS. And that's good enough for band gap. Okay? Okay, so basically, but the real bipolar, right, the NPN devices, they actually have better noise performance. Okay, they have low flicker noise, and which is maybe 1, 10, or 100 times smaller than the MOS. Okay, which is why the early high performance analog circuits are all bipolar. Okay, and today, if you buy some of the discrete components analog circuits, right, op-amp or reference or current source, whatever you buy from TI or these people, right? They are still the most high performance ones are still bipolar. Okay? Only problem is that these things cannot be integrated. You want to build a SoC, right? You cannot integrate these things because the technology is incompatible. Okay, so for MOSFET, the main advantage is that because it's a gate, right, the input impedance is very high. Okay? And therefore, input is very high, the current noise is low. Okay? Okay, filtering, I think quite straightforward, okay? you just filter out what if there's a noise somewhere, you just filter it out. If you know where the noise frequency is, you just filter it out. Okay? So if you have 1 level F noise or even some DC and your signal is not at low frequency, right? It's sitting on some carrier, you just filter out these guys, like use a high pass filter them out. Okay? So if your power line, noise from your power line is at 50, 60 hertz, you can use a notch filter. Notch filter is a filter that has a notch at certain frequencies. Right? So you can design a notch filter with a 0 at 50 hertz or 0 at 60 hertz. Okay? So, or you can just use a low pass filter to remove high frequency noise. Okay? Okay, so from a noise point of view, you want your circuit to have as small a bandwidth as possible. Right? Because you know the noise proportional to the bandwidth. Right? Noise normally is wideband. So the wider your circuit noise bandwidth is, the wider the bandwidth of your circuit is, the higher noise is going to be. Right? So don't design a very high bandwidth circuit if you don't really need to. Okay? You have higher noise, you need to burn more power. Okay? Okay. So sometimes if you want to minimize the application bandwidth, all right, so as to reduce the noise, right, and you want to maximize your signal bandwidth, you may need a high order filter. Okay, all right. This means the filter is complicated lah. Okay. Finally, this last point, I think it's quite obvious lah. If you're going to use a filter, you better be careful your filter doesn't inject more noise. Okay? So remember, if you just use a simple RC filter, there's noise there already. Okay, the R has got noise. Okay. Okay. You can do this kind of circuit, which is called frequency selective feedback. Okay? So, this is an interesting type of circuit, right? Because it's a feedback circuit, and if you analyze this circuit, right, if you put a low pass filter, all right, in the feedback path, and you go and look at what is the actual transfer function from output to input, okay, it actually becomes the overall becomes a high pass. Okay? All right? So I repeat again, this is a feedback circuit, right? And if you put a low pass in this feedback path, when you go and look at the transfer function from output to input, it looks like you have a high pass characteristics. Okay? Right? And actually, we already saw this in the delta signal converter. Remember? The delta signal converter also has a feedback path. Alright? And in the forward path, we put a low pass filter. Alright? The A of S, whatever. Alright? And we found that actually what this does is that it makes the noise transfer function become high pass. Remember? We shape the quantization noise, right? Because we put a low pass in the forward AS. When we do the analysis, the quantization noise transfer function actually has a high pass. Okay, all right. So this is nothing magical lah. So this kind of feedback system, depending on where you put certain blocks, the frequency characteristic at output is different. Okay. Okay, so now we'll talk quickly about this, how do we reduce noise that's sitting near DC or low frequency? Okay, we talked previously that, okay, for MOS, if I use a big WL, right, I can reduce the flicker noise. Okay, but I think circuit engineers have also come up with quite interesting concepts, okay? Things like auto zero. auto zero. Okay, what is auto zero? Auto zero is very simple, right? Basically, what it means is that if I can figure out some way to store the noise voltage, right, or store the offset voltage, right, and then I can cancel it. Okay, yeah, right. So this is the interesting concept, right? Right. So if I have offset and the 1 over f noise, we can sort of look at it like it's sort of like an offset, okay? It's not really DC, but it's got low frequency component, right? So it looks a little bit like DC, right? It's not exactly, but it looks a bit like DC. So the concept is, if in one cycle I store it, in another cycle I cancel it out. Okay, all right. So this is something that MOS can do that bipolar difficult to do, right? Because MOS, you can use it as a switch. The switch, I can sample things, right? Okay. So auto zero is this concept. Somehow I store it and then I cancel it, subtract it out. Okay. Another concept is what I call correlated double sampling, all right, which is actually similar to auto zero. Okay, the same concept is we try to store the offset, store the noise in one cycle, and then cancel it, use it to cancel on the next cycle. Okay. Chopper stabilization. Okay, what is this chopper stabilization? Is there a circuit? No circuit shown here. Okay, but this is another interesting concept. I think it's already existing for 20, 30 years already. Okay. So when the early op-amps were designed using MOS, right, they had very high offset voltage compared to the bipolar, right? The early generation designed using bipolar, offset was quite low, okay, microvolt, tens of microvolt. And then they started to use MOS and find that, oh, all the offset now is tens of millivolt now, right? So how to use now? I have applications that require microvolt, and now you give me an MOS amplifier that has millivolt kind of offset. Okay, how to use in high precision applications. So some bright guy came out with the concept. Chopper stabilization basically is how to say now. Basically, it's a very interesting concept that you use feed forward. You know, you use feed forward to suppress the amplifier offset. Okay. There's no way to draw this. Okay, anyway. So basically you have a main amplifier, you have an auxiliary amplifier. Okay? And you use the auxiliary amplifier to have a feed forward path. Right? That makes the main amplifier offset get smaller. Okay, that's the basic concept, okay? Of course, then they run the question, they run the problem, right? Okay, I can use the auxiliary amplifier, but this auxiliary amplifier also got offset. You know, right? So the concept works very well if I have a very low offset auxiliary amplifier. So then, of course, the concept is auto zero lah. Auto zero this guy. Auto zero the auxiliary amplifier so that it's got very low offset. Then use it in a feed forward path to do the chopper stabilization. Okay? If you're interested in this, you can kind of talk to me further, all right? Or you can just Google chopper stabilized amplifier. There are a lot of papers there that describe this thing. Okay. Another concept is, okay, switch out the transistor once in a while. Okay, and this will help to reduce the flicker noise. Okay, this one I think is not so practical for analog circuit because you cannot really switch your amplifier transistor off. Okay. Okay. We're almost there. Sorry, hang on for a while. Okay. So, oversampling, I think we really discussed in lecture 7. Okay, how to reduce in this case now, is the KT over C noise. Okay? In lecture 7, we talk about how to reduce the quantization noise by oversampling. Okay? Same concept applied to the KT over C noise. Okay? The KT over C noise, remember, comes about by sampling, right? Because you're doing a sampling on a capacitor. Alright? So, the sampling switches the resistance. It will cause a noise to be sampled on a capacitor, and it's called a KT over C noise. And this noise looks a bit like the quantization noise in that depending on what is your sampling frequency you choose, you can spread the noise out over the sampling frequency bandwidth. Okay? Okay, so you can see here, depending on whether you use a low frequency or high frequency, right? You can spread the noise out. And then, if I use a digital filter at the end to reduce my noise bandwidth, I end up with effective lower noise. Okay, so this technique is also used, right? Okay, so OSR is oversampling ratio. Okay, that means if I sample at a much higher frequency than I really need. Okay. Okay, but once again, this thing is nothing is for free. Okay, right? There's always a price to pay. Okay, so you know that during sampling, the sampling jitter is very important. Okay, so the sampling jitter will cause error in your SNR. Right? So if you sample at very high frequency, it means that your sampling jitter has to be better, more control. Okay? Which means that your sampling clock circuitry all becomes more complicated. Okay? Okay, this one is the noise shaping. This one we discussed in lecture 7. Okay? Is that if you can shape the noise, this is the example of quantization noise, right? In lecture 7. The quantization noise by itself is, we say is white, equal probability, uniform distribution. But we go through the sigma delta modulator, there's a shaping that suppresses it at low frequency and push most of it out to high frequency. Okay, this is what I call a noise shaping. Okay, so the original noise was white, but then go through the sigma delta or delta sigma loop. It has a noise transfer function that looks like this. Okay, suppress it at low frequency, push out to high frequency, but then we come in with a digital filter and just filter out all the high frequency part. Okay, so this is the concept that's mentioned here. Okay, right? Okay, so this is the exact delta sigma loop here. Okay, here is the condensation noise added here. Okay, all right. So you see, this is the signal transfer function. If AS is for low frequency is very high, much greater than 1, the signal transfer function is almost 1. Okay. But the noise transfer function, which is V out due to Vn, has a high pass, okay, right? Because this is approximately 1 over A. And if A is low pass, 1 over A is high pass. Okay? Yeah, so this is basically a review of lecture 7, right? This is your A of the delta sigma loop quantizer, feedback D to A. All right, this is a linear model. Okay, this is non-linear. This is a linear model. Okay, all right. This is the transfer function of the loop filter. All right, and then you can see that it has a high pass function. Okay, signal transfer function almost 1, noise transfer function high pass. Okay, and high pass depending on the order of this guy of the loop filter. Okay, and this is higher order, the shaping is more aggressive. Okay, right? Okay, so this is a summary. All right, we talked about noise power and we normalize it to 1 ohm. Okay, we talked about the time and frequency domain view of noise. Okay, and we always talk about the average noise power. Okay, we don't talk about average noise voltage because 0. Okay, average noise voltage will be 0. Right? we talk about how to integrate over the bandwidth the NSD, the noise spectral density, to find the noise power, and then we can find the RMS. Okay. We talk about what's the equivalent noise bandwidth. Single pole, what's the equivalent rectangular filter, okay, of this single pole, right? And then noise, how do we use different units? dBm power, dBc carrier, or dB volts, right? So this one is, what is the reference for dBm? 0 dBm means how much power? 1 milliwatt, okay, very important. You want to memorize, just memorize this one, okay? Okay? dBc is the power of the carrier. dBV, they have to tell you, okay, what is 0 dBV, okay? And then we talk about input referred noise, okay? Always try to simplify the circuit. So main circuit is noiseless. All the noise refer back to as a model as the input side, okay? And then we talk about different noise sources due to different components, all right? Thermal noise, we talk about KTOC noise due to sampling. The noise due to BJT, MOSFET, and op-amp. What's the different model, there's noise model that's used. Okay, this is very important. Know how to calculate the noise or estimate the noise. Right? We go from each noise source to the output. Okay, compute the noise at the output. After that, you can use transfer function to refer back to the input. Okay? Because sometimes we just want to know what is the input referred noise. Okay? Alright? And then we had some discussion on what some technique can use to reduce the noise. Okay? Okay, any questions on noise? Please try to understand this, right? Because homework 5 will be on this topic. Okay? And almost every year there will be one question or part of a question that will be asking about noise. Okay? Because because when you ask about noise, you will be asking you to identify where the noise source. You have to know how to analyze the circuit to find what is the bandwidth to calculate the noise. Okay, so it's a very good topic to integrate all these different topics in. Do you understand noise? Do you understand the circuit or the transfer function? Do you understand what is the bandwidth of your circuit to calculate the output noise? And do you know how to refer? Once you know a transfer function, you know how to refer back to the input. Okay, so it's a very, you can apply to many different questions. Okay, different amplifier circuit, everything. Okay, so almost every year, okay, every year there's one question or part of a question that will talk about noise. Okay. Okay, any final questions on noise? Okay, if not, please look through the slides, send me the question, I'll answer the questions. I will also, I think, post the homework 5, I think tomorrow. And I'll give you guys 2 weeks, enough time, 2 weeks? Okay, okay. Okay, so those who haven't had it submitted your homework 4, please, you still got 2 hours, okay, 2 or 3 hours. Okay, thank you. Yeah, no problem. No. Before, no.
You will just cover out the previous one.
Yeah. I mean, you can do anything you want before 11:59.
So you just take the last submission.
Yeah. I mean, you help me, you just delete your unwanted version. Yeah. Make sure you only leave one version there. Otherwise, I got to go and find out what is the latest version of this, right?
Then I have one question.
Yeah.